Yes, good morning. Laurent's Theorem Lesson 5. Example. Show that if C is positive, then Fz is equal to e raised to the power z plus c cube over 2z square is equal to summation which starts from minus infinity to infinity a n z the power n, where the coefficient of z the power n, that is a n, this is equal to e raised to the power minus c by 2 over 2 pi c raised to the power n integration which starts from 0 to 2 pi on e raised to the power c cos theta plus cos square theta, this is in bracket, into cos of c sin theta into 1 minus cos theta minus n theta d theta, right? So let's start with the solution. Since fz is analytic everywhere except, yes, except, just check your function fz where the function is not defined at z equal to 0 and infinity. Very good. So fz is analytic everywhere except z equal to 0 and infinity. So therefore fz is analytic in the analysis mod z lying between small r and capital R, which is again positive, and capital R is less than infinity, where r is small and capital R is large. Thus, fz can be expanded in the Laurent series in the analysis mod z lying between small r and capital R, right? We say like this. Hence, by the Laurent's theorem, we know that fz is equal to summation n going from minus infinity to infinity a n z the power n. This we know. Where we also know that the coefficient a n is equal to 1 over 2 pi iota integration over c1 fz over z the power n plus 1 dz, where coefficient is this in accordance to the Laurent's theorem. And what is the circle given to us? We have given mod z. Let's take this to be equal to c. We have taken c here because in question we have c. So take mod z is equal to c. So this is equal to 1 over 2 pi iota integral 0 to 2 pi, and the value for fz, it's given to us e raised to the power, wait, first write c1 only because we are not putting the value for z in this step. We're just writing the value of the function, that is e raised to the power z plus c cube over 2z square over z to the power n plus 1 dz. In the next step, we are going to put the value for z. Z is equal to, yes, c e the power iota theta, and dz will be iota c e the power iota theta d theta. Very good. Let's put the values of z. So this is equal to 1 over 2 pi iota integration from 0 to 2 pi, because now we are using the polar form of z. So this is e raised to the power, instead of z write c e the power iota theta plus c cube over 2 z square. So z square will be, I'm taking z square to the numerator, so this is e the power minus 2 iota theta over c square, and dz will be c iota e the power iota theta d theta over z square plus 1. Oh, sorry, z the power n plus 1. So this will be c the power n plus 1 because z is c e the power iota theta. So the power n plus 1 will be c the power n plus 1 and e the power n plus 1 iota theta. Clear? Alright. In the next step, 1 over iota cancel, and this will be 2 pi c the power n, 0 to 2 pi, because c is also cancelled with the numerator. So this is e the power c e the power iota theta. Again we have to cancel c square. We get c e the power minus 2 iota theta over 2. And in the denominator we are having e raised to the power n iota theta. E raised to the power iota theta is also cancelled with this numerator. Fine. Next. So let's collect all the coefficients, let's collect all the powers of e. 2 pi c the power n, 0 to 2 pi, and collecting all the powers of e. So this is c e the power iota theta plus c by 2 e raised to the power minus 2 iota theta minus n iota theta d theta. Now what we have to do is, we have to change this e the power iota theta into cos of theta plus iota sine of theta. I'm taking this as, let's take, because again and again we have to write, let's take this to be equal to t just for this to solve the further steps. So I take t to be equal to c e the power iota theta plus c by 2 e raised to the power minus 2 iota theta minus n iota theta. Now this is equal to c. This is cos theta plus iota sine theta plus c by 2. This is cos 2 theta minus iota sine 2 theta. Minus n iota theta. Fine. Now next step is collect the real parts on the one side. So we get c cos theta, and real part from the second term is plus c by 2 cos 2 theta. And now collecting the imaginary parts. This is sine theta, c sine theta minus c by 2 sine of 2 theta minus n theta. Right? Up to this. Now, let's put this value back in this e raised to the power t which we have taken. Put this value back over here. We get one over 2 pi c the power n integration 0 to 2 pi e raised to the power c cos theta, taking c common, plus half cos 2 theta e raised to the power iota, this is one and the same thing, c sine theta minus c by 2 sine of 2 theta minus n theta. I hope this step is very clear to you. Now 1 over 2 pi c the power n, 0 to 2 pi. This is as it is, cos theta plus 1 by 2 cos of 2 theta. Let this remain as it is. And now again e raised to the power iota, this is whole angle. So what we have to do is again change this to cos of iota theta plus iota sine of theta. So this will be cos of theta, where theta is c sine, the other angle, c sine theta minus c by 2 sine 2 theta minus n theta, like this. So this is c sine theta minus c by 2 sine of 2 theta minus n theta. This plus iota sine of, again whole thing, c sine of theta minus c by 2 sine 2 theta minus n theta with d theta. E raised to the power iota theta is equal to, I am using this, cos theta plus iota sine of theta again and again. Now in the next step, just separate this integral. Take the integral with the real part and the integral with the imaginary part. So this is 1 over 2 pi c the power n 0 to 2 pi e raised to the power c cos theta plus 1 by 2 cos 2 theta into cos of c sin theta minus c by 2 sine of 2 theta minus n theta. This is one integral, right? D theta. Plus again the integral with remaining the imaginary part. So this is iota over 2 pi c the power n 0 to 2 pi e raised to the power c cos theta plus 1 by 2 cos of 2 theta into sine of c sin theta minus c by 2 sine of 2 theta minus n theta d theta. Right? Mark this as your 1, and we need to have now? This second integral. We need this integral to be 0. And why this integral will be 0? Because we need to check f of 2 pi minus theta should come as minus of f theta, right? If suppose this is your homework, just take this as your assignment. You put f of theta to be equal to, that is your second integral, e raised to the power c cos theta plus 1 by 2 cos 2 theta sine of c sin theta minus c by 2 sine of 2 theta minus n theta, right? This is your f theta. You need to check what is f of 2 pi minus theta. So you have to put, instead of theta, 2 pi minus theta and check the value. That will comes out to be minus f of theta. And whenever this thing happens, we say that integration is 0. So what we are left with? So integral, the second integral, e the power 2 pi e raised to the power c cos theta plus 1 by 2 cos of 2 theta sine of c sin theta minus c by 2 sine of 2 theta minus n theta d theta. This whole integration is equal to 0. So from 1 we get our an is equal to 1 over 2 pi c the power n 0 to 2 pi e raised to the power c cos of theta plus 1 by 2 cos of 2 theta into cos of c sin theta minus c by 2 sine of 2 theta minus n theta into d theta. Now the next step. What is cos theta? Yes. this is equal to 1 over 2 pi c the power n 0 to 2 pi e raised to the power c cos theta. Yes. What is cos of 2 theta? This is I'm very sorry, this is cos theta plus half cos theta. Right. Yes, cos theta plus half cos 2 theta. What is cos 2 theta? It is 2 cos square theta minus 1. So this is, I'm writing over here, cos 2 theta is equal to 2 cos square theta minus 1. So using this, cos of 2 theta by 2 will be 1 by 2. Cos 2 theta is 2 cos square theta minus 1. Into cos of c sin theta minus c by 2 sin of 2 theta minus n theta into d theta. Alright. Next step, I'm inserting one page. Now in the next step, 1 over 2 pi c the power n 0 to 2 pi, just open the bracket, e the power c cos theta plus this is cos square theta minus 1 by 2. Now it's easy. Rest cos of c sin theta minus c sin theta. Okay. Instead of sin 2 theta, what is sin of 2 theta? This is 2 sin theta cos theta. So 2 cancel. I'm writing c sin theta cos theta minus n theta d theta. I have used sin of 2 theta as 2 sin theta cos theta in this step. Next, 1 over 2 pi c the power n 0 to 2 pi e raised to the power c. This is cos theta plus cos square theta. And this is e raised to the power minus c by 2. I'm taking that outside. It's a constant, e raised to the power minus c by 2. Taking outside. So remaining cos of c sin theta, which is common from here, 1 minus cos theta minus n theta. Very fine. So this is what we require, right? Hence, this is our required coefficient an, which we have to prove. So hence, e raised to the power z, which is our function, c cube over 2z square fz, which is our function. This is equal to, we have proved, minus infinity to infinity a and z the power n, where an coefficient is equal to, we have proved, e raised to the power minus c by 2 over 2 pi c the power n 0 to 2 pi e raised to the power c cos of theta plus cos square theta into cos of c sin theta into 1 minus cos theta minus n theta d theta. That's about this proof. Easy, very easy. Just a little bit lengthy, but steps are very clear, alright? Don't worry. Next, there is a remark. fz is equal to, how we can the other way of using fz as, this is equal to 0 to z f dash t dt plus f of 0. If you solve this, you will get, what is the integration for f dash t? That is ft, right? Then limit 0 to z plus f0, which is equal to, putting the limits, upper limit minus lower limit. So this is f of z minus f of 0 plus f of 0. This is cancelled. We get fz. So there is another way of writing fz to be equal to this. And now in this example, I'm going to use this way, right? This is a short example. Example, expand fz is equal to log 1 plus z in a Maclaurin series valid for mod z less than 1. Solution. So let our fz is given to be, that is equal to log of 1 plus z. Then let's check our f dash z because we need this. So this is 1 over 1 plus z, which can also be written as 1 plus z the power inverse, which is expanded as summation n going from 0 to infinity minus 1 the power n z the power n. And why I have expanded this is the condition given to us that mod of z is less than 1. Let's check. Yes, it is given to us. Mod of z is less than 1. That's why we expand this 1 plus z inverse. Otherwise, you cannot expand. You need this condition, right? For mod z less than 1. Now next, log of this function, that is f of z, can be written as fz, which is equal to 0 to z. I'm using that remark, f dash t dt plus f of 0. So this is equal to 0 to z. What is f dash? If we write in t, what will be this? This is summation n going from 0 to infinity minus 1 the power n t the power n dt, right? Plus, what is f of 0? We put 0 over here. We get log of 1 plus 0. That is log of 1. Clear? Which is 0. So this is equal to, now taking this summation outside, n the power 0 to infinity. Why I'm taking this summation outside? What is the reason for that? Log of 1 is 0, yes. What is the reason for that? Why I take the summation outside? Because the convergence being uniform. If the series is uniformly convergent, then only we can take our summation outside, right? So the reason is the convergence is uniform. It is uniformly convergent if you use your V-STRAS-M test. So whenever you need to put summation outside, just check the series is uniformly convergent or not. So after this is equal to summation n going from 0 to infinity minus 1 the power n. Yes, what is the integration for t the power n? This is t the power n plus 1 over n plus 1 with limits 0 to z. So this is equal to n going from 0 to infinity minus 1 the power n z the power n plus 1 over n plus 1 minus 0. So we get n from 0 to infinity minus 1 the power n z the power n plus 1 over n plus 1. That's it. Short example, right? Okay. Here is a remark for you. Just in this example, we have chosen the principal branch, so that capital principal branch, whenever we use the word principal branch, that means we are talking about capital L, log, right? And that log 1 is 0. So more generally, when log of 1 small l, log of 1 is equal to 2m by iota, where m is your integers, right? M belongs to the set of integers. We have log of 1 plus z is equal to fz. So we have small log 1 plus z is equal to 2m pi iota. We just need to add this extra term 2m pi iota. That's it. If you use the word small l, because in this example we have used capital L, we have used the principal branch, and log of 1 is 0, right? But here, if you are having small l, you just need to add an extra term 2m pi iota, then plus summation n going from 0 to infinity minus 1 the power n z the power n plus 1 over n plus 1 as your result, right? So we just proved that this capital log of z, right? This is summation n going from 0 to infinity minus 1 the power n into z the power n plus 1 over n plus 1. This is the value for your capital log of 1 plus z. But if you look at the value for the small l, log of 1 plus z, that is equal to 2m pi iota plus summation 0 to infinity minus 1 the power n z the power n plus 1 over n plus 1. This is very important. Second remark is, if you look at your sine z function, you will get the result as summation n going from 0 to infinity minus 1 the power n over 2n plus 1 factorial into z the power 2n plus 1. For cos z, you will have summation n going from 0 to infinity minus 1 the power n over 2n factorial into z the power 2n, right? And remaining log of z, that is your natural log, not 1 plus z, only log of z. So you will get summation n going from 0 to infinity minus 1 the power n into z the power n plus 1 over n plus 1. This is the value for the principal branch log of z. Thank you for watching this video. Next time we will be doing singularities and Cauchy residue theorem. Just get ready for that. Do subscribe the channel for latest videos. Thank you.